So our next experiment, eighth experiment, is to design and simulate our Cmos basic gates and flip-flops. So completely in a digital flow. The same thing we followed for our last experiment we are going to construct. So for that we have to open this DSCH2. So I have constructed a circuit schematic for our OR gate, and after that I have to check this. So I'm going to run. So after it, while it is running, we can change the input as well. So whenever both the inputs are high, we are getting the high output by LED glowing. Then again, if I change one input, the answer will be 0. Similarly, when both the inputs are 0, the answer will be 0. So we can check the timing diagram also for the same. And now we have to construct a construct a Verilog file. So for that, we can move to file. Can close this one and open file. Make Verilog file. So here in the path, say new folder new.or.sch. So this is the Verilog file which is created based upon our schematics. So we are giving OK. Now we are going to minimize it, and then we have to move to microwind tools. So here MW tools. Now export microwind. So you have to open, and here you have to choose microwind 2 and run as administrator. Yes. Now have to compile Verilog file. Click compile and choose compile Verilog file, and then here you can found, which is already I have browsed, so it is available in the directory. So this is the Verilog file which is constructed from our schematic. So I'm going to open it, and here you can found this, and while scrolling to the down, and you can get this button compile. Click that and back to editor. So this is the layout for our OR gate, basic OR gate. So this OR gate layout we have got from our schematic, and then now I'm going to run it, run simulation. So you can check the voltage versus timing diagram for our OR gate. So whenever both the inputs are 0, we are getting the output of 0, and whenever both the inputs are 1, so you can check here 1 and 1, we are getting the answer as 1. Similarly, the power it is consumed is 7.925 milliwatt. So you can also check the behavior of the circuit while voltage and current are given, as well as voltage versus voltage, and then frequency versus time, then I diagram. So this is the way you can construct construct and check the post layout and pre-layout simulation for our basic gate, which is nothing but OR gate. Similarly, I am going to do the same thing for our next gate. So here NAND gate I am going to do. So open NAND gate. So the same concept we are going to perform. So I'm going to run, and I'm going to change the input conditions. So when both the inputs are high, we are getting the lower output. So when I change the input to 0, here also I'm getting the 1 as the output, and when both the inputs are low, here we are getting the higher output. You can check the graph parallelly, and then the same thing we are going to perform. So what it means, we have to compile and make a Verilog file. So choose Verilog file. So now a module of Verilog file is constructed for our schematics, so which is available in our directory, new folder, new nand.sch. So you have to click OK, then you have to minimize and keep, and you have to again open this microwind 2 and run as administrator. You have to give S, and then have to close all this and move to compile. Choose compile Verilog, and here it is NAND. So you have to open that NAND, and you can check your file here. Verilog file is here, and then scroll down and click compile, and again click back to editor. So we can get the layout of our basic NAND gate. So this is our layout. So after this layout, we are going to perform simulation, which is called as post layout simulation. So for that, I'm going to check this run simulation button. So here we can get the output voltage versus timing, that is there, it is its performance, and all other timing reports, as well as voltage versus current, frequency versus timing, and eye diagrams. Now also we can see the power dissipated also. P is equal to 7.4774 millivolt. So here simulation time we can check here, 4.94. So next thing we have to perform is our flip-flops. So for that, which is already I have drawn, so I'm going to open D flip-flop. So I have already constructed this D flip-flop. So this is the D flip-flop. This D register I have got from our symbol library, which is directly available. So also here for a clock pulse I have given a clock pulse trainer, and as well as in the previous case we have constructed as using the input button. So same thing I have did here. Also for output we have kept the output. So I'm going to run this, so we can check the schematic as well. And then now the same thing we have to do, which is nothing but make Verilog file for our D flip-flop. So I'm clicking OK. Now we have to open this microWin 2. Okay, you can close the previous one. Okay, you can open a new one. Export microWin. Run as administrator. Yes. Then you have to choose compile. Select compile Verilog. So here it is D flip-flop. This is the file we have to open, and you can check here your Verilog file coding, and then click compile, and now back to editor. So this is the D flip-flop layout, so which we have constructed using our schematic. So then after this layout is constructed, we have to check the simulation. So I am running the simulation file. So clock pulse also we are getting, and input 1, input 2, and output. So this is the voltage versus time, and our power result is also available, and our timing report also available. You can check the eye diagram as well, frequency versus timing diagram, and voltage versus voltage. Now we are going to construct the NAND gate using Cmos logic, and after that we are going to perform post layout simulation and pre-layout simulation, and analyze the power and timing diagrams. So for our NAND gate using Cmos, we need two PMOS devices and two NMOS devices. So first of all, I'm going to drag and place the PMOS, and now the two PMOS symbols I have placed, and if we click that symbol, and we can see the show. Here you can choose the show pin names and pin numbers. So using that we can easily identify the source, where the source port is available, as well as where this drain port is available. So for that you have to just click that symbol, and here you have to check the boxes, show pin names and show pin number, show symbols. You OK. So after that, then I'm going to move further. Then we need two NMOS devices for our NAND gate. So I'm going to click the NAND gate and drag. So for this also we need to know the symbol as well as pin names. Okay, which will be easy for us to connect the two gates, so that we are doing this. Okay, now we have to connect both the drains of our PMOS. So I'm going to use the command line and connecting the drain of both the PMOS, and after that we have to connect both the source of our PMOS. So I'm connecting. Then we have to connect the I'm going to connect the drain of our NMOS with the drain of our PMOS. Then we have to connect the source and the drain of our both NMOSes, and now we are going to give the input. So for that we need to have a button symbol. So it is here. We can have to track and keep. So input 1 and input 2. So let me move this here and we can place here and place here. So for CMOS construction of our NAND gate, we need to combine a PMOS and NMOS and together to give us input 1. Also for our another input we need to do the same concept. So for that I have to connect both the inputs of our first PMOS and our last NMOS. So with this connection I am going to connect the input 1, and after that I am going to connect the PMOS 2 with the NMOS gate. See how to delete this. For this we can use this gun symbol, cut. So it will cut the construction, and after that go back to draw and then have to move this one. So we can move this, and after that I'm going to add a line. Okay, then this additional symbol I can cut, draw, click draw, and then use this command line. Now you can connect the input 2 with this interconnected lines. So now we have connected all the inputs. Now we have to take the output. The output should be taken from the middle portion, which is nothing but our PMOS and NMOS circuits are connected. In the upper portion is composed of PMOS and lower portion is composed of NMOS. Between these two symbols we have to place our output. So for output we are going to use LED bulb. So I'm going to keep that here and connecting the output wire. And now we have to place the source symbol in the center and the ground symbol for our symbols. Okay, now I'm going to save this. Save as CMOS NAND. Save. Okay, I can run. So I can change the input now. So when both the inputs are high, which is nothing but 1 1, when both the inputs are high, we have to get the output as 0, which can be indicated that the LED is not blinking. Now suppose if I change the input to 1 0, I can get the answer as 1, and again now when I change both the inputs to 0 also, I am getting the answer as 1. Now the operation is succeed. So this indicates our constructed NAND gate is correct, and we can check that using our timing diagram. So here it is our timing diagram, and after that we have to construct the Verilog file. For that I'm going to choose file. In file I can click make Verilog file. Here the Verilog file is created for our CMOS NAND gate, and here this file can be found in this directory, C new folder new and CMOS NAND, which is created by me. So you can simply set your own directory. So please remember the directory, which will be helpful for us while compiling this Verilog file in our microwin tools. So click OK. Now I have to minimize this and I have to open microwin tool again, and here MW tools. Now I'm going to choose export microwin. Here click microwin 2 and choose run as administrator, give yes. Here now the layout window opens, give close and choose compile option, and select compile Verilog, and here you can see CMOS NAND gate. This is the Verilog file we have constructed using a schematic in the previous window. So I'm going to choose that and I'm giving open, and we can check that. And when you scroll down you can find the option as compile. You have to click that, and back to editor, and we can now see the layout for our Cmos NAND gate, which is nothing but NAND gate, which is constructed simply using Cmos and NMOS. And now for this layout, we can check the post layout simulation by clicking the green color play button, which is nothing but our run simulation, and you can check the same. So as usual, in the schematics we have checked the same truth table operation. Here also you can check when both the inputs are 1 and 0, we can get the output of 1. And here power also we can check 1.23 millivolt, and voltage versus current, and this is our voltage versus voltage waveform, and frequency diagram and I diagram. So this is the way we can analyze the post as well as pre-layout simulation for our CMOS NAND gate. So similarly for our flip-flop, we can see how we can construct our SR flip-flop and verify the same. So I'm going to close all this, close the program, and now I'm going to open my schematic window, and I have to create a new window. So there now I'm going to construct our SR flip-flop. So for this we need a NAR gate. So first I'm going to browse the list of symbols, symbol library. So view, we can click this symbol library. So I need gates. So here this is our NAND 2 input NAND gate. I need 2 input NAR gate. So I'm moving on. So here it is our 2 input NAR gate. See, I'm placing this. Now we are going to create the schematic for our SR flip-flop. So for this I'm going to use NAND gate. So using the symbol library I can browse and get the NAND gate, 2 input NAND gate. So I'm placing it here, and again we need a NAND gate. So that also we can place here, and 4 NAND gates we need. So I'm going to track and place 4 NAND gates. Then we can minimize even. Okay. Then what you have to do is you have to connect both the inputs of our first NAND gate. So I'm going to connect those. Connected portions. And then here also we are going to connect. Now we can give the inputs. Input 1, which is nothing but our S input. We can click by changing the name S. Okay, and then you have to connect those with our gate. Okay. Go to draw. Then we need another input, which is nothing but our R input, reset input. So for this also we are going to use the reset button. I'm going to click that, and I'm giving the name as R. Okay, then click line and connect those with the second NAND gate. And after that we have to give the input to our third NAND gate, and we have to interconnect both the gates of our second gate's input, and connect the output of our first NAND gate with the second NAND gate. We have to place a output LED here. So for that I am giving extension. Then you can go for LED. Here also again we need an LED. We can change the symbol name even. So you can rename it as Q. Okay. Then here also you can rename. You can just double click it and you will get the option to rename. So Q bar, it is the output for our second. Then we have to interconnect the outputs. So for that we need simple gun to remove the existing, and you can connect the one of the input to the output of the first NAND gate. Similarly the same thing, click draw and okay. Now it's ready. You can just rename the circuit. So you can rename the circuit by giving the names. Show pin names, pin numbers, show name as symbol. Checklist. Similarly here also, pin names, symbol, pin number. Okay. Okay, now we are going to save this file. Save as Cmos, SR flip-flop. SR flip-flop. So I'm going to save this, and now I'm going to simulate. And if I change the input, you can get the answer in the queue. And when both the inputs are S and S as well as R, both the inputs are high, we are getting the Q and Q bar getting the high output. When the set is 0, we are getting the output only in the Q bar. When reset is 0, we are getting the output. So we are verifying the truth table. After that, we can check the timing diagram. And now you can, as usual, you can go to file and choose make Verilog file. You can see the Verilog files created. Click OK. Now minimize it and you can move on to our microwin tools. In microwin tools, select MW tools and click export microwin. Here choose microwin 2 and now close this one. And in the editor window, open compile and click compile Verilog, and then you can get the Verilog file for our SR flip-flop and click open. You can check the Verilog file here and scroll down and click compile Verilog. Click back to editor. Oh, this is the layout for our SR flip-flop. So you can check the post layout simulation by clicking the run button. So you can see the S input as well as R input and Q bar characteristics, and also voltage versus current, voltage versus voltage, and then the frequency versus timing and I diagrams, and also the power. Power report shows 13.35 millivolt. So this is the way you can easily construct the pre layout and post layout simulation using the schematics microwin tool.